Good morning, everybody, and welcome back. So today, as we also announced through the email, we are going to have Eric, who will say a little bit about how they developed the convolutional neural network code. So I just wanted to say something about the programming languages we end up with, strategies for writing codes, etc., etc. So many of you will end up using PyTorch, and the textbooks which we have access to, like Sebastian Raschka's book and also David Foster's book, they allow you to download the source files, the Jupyter notebooks, for every single chapter. That means that you can look at both examples written with TensorFlow/Keras and with PyTorch. So Sebastian Raschka's book and collaborators, that uses extensively PyTorch. And I know that many of you are interested in doing that. But then we do also have people who want to write their own code. So this is one of the options for the projects. And we have a group of people who want to write their own CNN code, but we also have groups of people who want to write their own recurrent neural network code. Now, the recurrent neural network machinery is something which we will start discussing today, and we will continue a little bit with that next week. But then the focus will be the examples which I will show will be on applications to differential equations. That means real-time series. If you're looking at language models, these are examples of data which cannot be assigned a timestamp. So there are many different types of applications of it. And the applications which we will discuss next week are more related to those of you who are interested in solving, let's say, differential equations or that type of natural science problems. And there's a main reason for that, is that I have never done research on, for instance, large language models. So that means that I would just be reciting what's in textbooks. And but for those of you who want to explore that possibility, this is something you can do with project number 1, and eventually also if you want to merge everything into one project. I also sent an email about projects and project length, etc. There is always some kind of uncertainty because on the website it says maximum 10 pages. This is also put there in order to have people to, because what happens often when you write these projects, they start to live their own lives. And many people take ownership. And we've had cases with reports of 40, 50 pages. Eric, who's here, is just one of these examples. And we love this. But the administration, also the study administration, wants people to see that there is actually a limit to what you can put into 10 credits. So the 10 pages is something which we are very, very flexible with. It's not that you get penalized if you write 10 and a half a page or 20 pages. So we want you to have this kind of freedom to explore things. So today, after this kind of introductory words, and just keep in mind that the topic of today comes after Eric's presentation. So Eric will say a little bit about the philosophy which he and Greg applied last year when they developed the CNN code. So Eric comes from the bachelor degree in robotics at the Department of Informatics, and he's now doing his master degree at the ETH in Zurich. So I'm going to give you my headset. That should you get my earbuds?
Hvordan scroller jeg på greia? Så scroller jeg på. Skal jeg bare gjøre det sånn manually?
Jeg skal hente den der, og så bare så jeg begynner koden.
Kjempefint.
Så da har du den. Ja. Okay.
All right. So hello everyone. My name is Eric. I flew in from Switzerland just to do this. And today I'm going to take you through my CNN implementation, which I programmed with the help of Greg, or Gregor Kaida. Before we get into the CNN code, I'd just like to talk about like a brief overview of what we wanted to achieve. We wanted to write a code that was very readable. So that was, I'm going to take out the earpods so I can actually hear myself. we wanted to build a CNN with a focus on readability, such that it could be used by people who wanted to interpret, like figure out what's actually happening in these layers. Now, could I get a show of hand of people who have actually used TensorFlow or PyTorch or anything similar to implement the CNN or just neural network in general? Perfect. So if you've done it before, maybe you've read the documentation, or maybe you've tried to actually figure out what each layer does. It's kind of confusing. You don't really know what it does. It's kind of this black box design, and you know some theory that's behind it. You understand the mathematics, but it's nice to get an algorithmic perspective as well. And that's what we've tried to implement here. So our code generally, before I get into it, takes a structure very similar to TensorFlow and PyTorch, where you have the CNN object and you can add layer by layer to it. The layers we have are convolutional layers, pooling layers, flattened layer, dense layers, which we call fully connected layers, and an output layer. Now, the first part here is about schedulers. Now, you might be familiar with these. We just made a general class for schedulers. This isn't the most important part, but it's just a nice, like we're just going to look at some of the different building blocks that we will need for our convolutional neural network before we actually get into the code. We've made an abstract class for schedulers, and this part isn't that important, but you can just see our implementation of, for example, the constant scheduler, a momentum scheduler, AutoGrad, AutoGrad with a momentum, RMS prop, and Atom. And they all kind of take the same form with an update change function and a reset function for those schedulers which need it. Again, this isn't the most important part, but we also wanted to make our CNN code very generalizable, such that you could use it with any given scheduler that you want and run some experiments with it, as we did in Physestica, which some of you might have taken. We give some examples here of what specifically a scheduler does. I'm not going to go through it here, but if you want to have a look, feel free to go through it. Similarly, we wrote up a bunch of cost functions, all of them taking the same kind of form when it comes to an algorithm. Again, I'm not going to spend too much time here, but just to know that you can use OLS, you can use logreg, and you can use cross entropy loss. And finally, before we really get into it, we also wrote an implementation for the different activation functions, which you can use in the neural network. Of interest, for example, would be softmax, which you would then use, for example, the output layer. Or really what you would use to implement some nonlinearity into some of your convolutional layers. Again, if you want to take a look at how we've implemented these, feel free to, but this is more of a background to what you can then implement and use with the CNN code. We've also given some examples here for convolution, but I think that theory has already been covered by lectures. And we also wrote up some examples of just applying a simple convolution, but again, I'm going to skip this. And this is Greg's dog, Luna, who we refer to as cute dog in our variables. Perfect. So now we actually get to a bit of the meat of the CNN implementation. So what we did is that we made an abstract class layer, which has a feed forward method, a backpropagate method, and a reset weights method. These are the three fundamental methods which all of our layers share. So all of our convolutional layers, pooling layers, and dense layers, any layer that we have will share these three methods. This is to get kind of the simple structure into our code and to get a nice overview. So if you're going to write your own CNN, it could be of interest to look at like what each layer actually takes as input and then serves as output. Here, we've decided to take input channels, feature maps, kernel height, kernel width, stride, that's vertical, stride and height, and a padding feature, which we'll talk about later, which activation function takes if you want to seed it or not, or if you want to reset the weights independently. This is very much a detail. If anyone has any questions about it and why we had to implement this, feel free to ask. However, if you're going to use this code to build your own CNN and just play around, you don't have to worry about these. Most of these get filled out by default arguments. But if you're writing your own code, it might be interesting to see what layer actually takes what as input. This is something that you can't really see in the mathematics of the code, and it's nice to get an algorithmic perspective on. So now we're in the convolutional neural network, and the feed-forward part of the network is probably the most interesting. As you can see here, we apply some concepts such as padding, which we have a method for later, which I can go through. We just set up here some stuff for the output. Again, these are more implementation details if you really want to be specific with implementing your own. However, I think the main interest here is the actual convolution, which we've written here to be interpretable and not effective. And one of the things you can quickly realize is that we have a nested set of for loops where we have 5 different for loops which are nested. Now, I think most people with a programming background can really immediately tell that this is horribly inefficient. And if you've looked at the formula for a convolution, you might not really be able to identify, at least personally, I prefer seeing it algorithmically, that this is a gigantic bottleneck. I mean, just looking at this, you can tell like, oh, this is going to take a long time. And actually, we've also provided a more optimized version of this code further down, which I will briefly go over. However, you get a nice intuition for what actually happens. You can see that we go through every image, through every input channel, through every feature map, through every like height and width pixel in the image, and then perform this, which is the convolution itself written in Python code. You can think of this code as kind of selecting here the parts of the height and width of the like the batch that you're currently working through of images, and applying the kernel to that specific window, which is the same size as the kernel. Now, you might see a bunch of these indices, and it might look a bit confusing. However, we hope if you're able to go through the code in your own time, we have written up which matrices have which indices, so it's a bit more interpretable. And we also hope that the variable names, such as like the first dimension being the images, the second dimension representing the input channels, and the third and fourth representing the coordinates of each image, that this is an intuitive and consistent representation across our entire code. Now, most of you probably know what the CNN does in the feed-forward pass. You pad the image, or you pad the images, and you convolve them. And then you send it through an activation function. However, for those of you building your own CNN, and I mean, could I get a raise of hand who has an interest in building their own convolutional neural network? All right, perfect. We've got some people. So you might know what the convolutional neural network does in the feed-forward pass, but you've probably never heard of what the convolutional neural network does in the backpropagation pass. I don't know if this was covered in the theory, but it's a niche topic. Most people kind of don't know what it does in the backpropagation pass. It's actually very interesting because what it does is just more convolution. You might be surprised to learn. You perform a convolution on 2 different gradients, one for the delta term, which you pass on to the next layer again, and another convolution which you use to update the weights of the kernel. And in writing this code, we actually learned a ton about CNNs. I mean, just going into it, we had kind of these concepts floating around of like, we have padding, okay, we have convolution, we have stride, and we have the different layers. We kind of had this overview, but we didn't really know the nitty gritty. We saw the wood for the trees, as Martin often says, but we didn't really go quite into detail. So looking at the backpropagation was really interesting. And again, if you go through it, you can see all of these for loops. You can also see how, for example, we had to tackle some interesting challenges, as if you use stride in your feed-forward pass, you now suddenly have a matrix that's been reduced in dimensionality. So when you pass it backwards through backpropagation, you have to regain that dimensionality. How do you do that? Well, here we implement some code that just like, it fills in the zeros for where we've strided, which is the best solution you can do. And further down here, you can see the convolutions again. And if you're like me and you think that having this many for loops is probably a bad idea, then you see also here that in the backpropagation pass, that it takes a lot of time, and you could probably do this more efficiently. Finally, I want to take you guys through the code for the padding. Now, actually another thing that you'd never think about is that you actually have to have a different type of padding for when you do convolution in the feed-forward pass for the images, and a padding for the gradient in the backpropagation pass. This is why I really recommend implementing your own CNN. It's just because there's so many cool details that you would never think about that are interesting and just fun to discover. Sometimes not that fun, but luckily now I hope this resource can be of help if you stumble into any of these problems. And feel free to ask me or Morten at any time about any of these implementation choices. Yeah, the code here. This is just the padding for the for the images, and the padding here for the gradients. But ultimately, what you do is just that you make a big zero matrix which has the padded sizes. And I saw in some of the lecture material that padding can be taken in as a parameter, correct? But however, here we just calculate it automatically based on the size of your kernel, which you can figure out by just like dividing it in half and I think flooring it. I don't remember it exactly. But we don't take it as a parameter, which might be a bit different from what you've learned in the theory, but is still a valid implementation. So if you guys want to read more about backpropagation in the convolutional layer, I'd really recommend this article on Medium. You can find it in this notebook, or you can just Google backpropagation neural network, and you'll find this excellent article, which takes you through the two different convolutions. And it's really interesting because you're actually doing differentiation. You're doing the chain rule, but it can be rewritten using some magic to be written in terms of a convolution. We give here a little demonstration, and actually I'm just going to run. Are the like code blocks already run? Okay, perfect. Yes. So again, we're just going to show this quick demonstration of like you can make your own convolutional layer. You can select your own amount of input channels, feature maps, whatever you want. Most of these arguments are optional. And if you just pass it through there, you can see that you can see what happens when you just run it through a convolutional layer forwards and backwards a couple of times, what it learns. And I mean, it's not very informative, but this is what happens. So now I'm going to move on to the pooling layer. First of all, are there any questions to the convolutional layer before I go on? It's probably a bit difficult to formulate questions because the code, like it's a bit difficult to just read it immediately when you only see a chunk of it. But again, if you have any questions, feel free to reach out. I'll gladly answer any questions. So the pooling layer, again, is used for reducing the dimensionality, and we've introduced both a max pooling layer and an average pooling layer. Again, we have a feed-forward pass, and probably most of you have some intuition about what happens in the feed-forward pass. We select some windows of our image, and we select either the max value or the average value, and we continue on with that. Now, I'm not going to go too much into detail here, but again, you can see that for pooling, you again have these nested for loops, and I probably sound like a broken record at this point, but I mean, you don't want this. And again, if you actually compare this to Stride, which you can just use directly in the convolutional layer for dimensionality reduction, you can probably tell that having this entire layer, which has to run through 4 extra for loops again, is probably going to be a bit of a slowdown on the system. However, I would take this with some grain of salt, as we've implemented this to be readable and not efficient. If you use TensorFlow or PyTorch or something, I'm not exactly sure how the Stride versus pooling runtime trade-off is exactly, but I would imagine it probably takes a bit more time to do pooling, which might be intuitive, because if you would look at the convolutional neural network code, Stride only makes you skip in the for loop, whilst pooling adds this entire section of nested for loops. Again, for those of you who want to implement your own, seeing what backpropagation does in the pooling layer is again one of those things that you kind of like never think about. And the answer in short is just that you kind of have to reshape the matrix that you use. And by the matrix, I mean your input with your input channels and your height and your width parameters. You just have to reshape your image or your set of images to be the same size as they were in the previous convolutional neural network. That's all it does, and you just fill out with a bunch of I think zeros. Oh, also one nice feature of this code, which I want to point out, is that if you want to play around with the code, which I'll show you a bit how to do later, we check for errors, meaning that if you make any mistakes or if you do something when you set up your code that's unintuitive, we will actually throw you error messages which are very specific to what mistake you've made. If you've used TensorFlow or PyTorch before, finding out what has happened can be a bit of a mystery depending on the error. We don't check for that many errors, but we really try to focus on the errors which would yield some learning opportunity, where it's like, oh, I made this mistake, and then we hope it gives you some intuition. Finally, we're at the flattening layer, and from here on out, we're going to be looking more at the classical neural network structure, which some of you might be more familiar with. And for any of you guys who are going to implement anything to do with a neural network, this part of the code will be very relevant for you. Or, well, actually, the flattening layer will be a bit specific to the CNN model. However, it's still interesting to look at. Again, in the feed-forward pass, we kind of treated the flattening layer as the first hidden layer in the neural network, which reshapes your matrix to be a flat array instead of this multidimensional image input channel height width data. And the backpropagation pass here is more what we're used to seeing in just a regular neural network. Also, something we try to do is keep the words of the variables, like the names of their variables, and some of the just like matrix names, like a matrix, consistent with the notation used in Morten's lectures. And if they weren't mentioned in Morten's lecture, we just tried looking across literature, but again, these variable names just sometimes change. So we hope it's all right. Yeah. Finally, I'm just going to go through the fully connected layers and the output layer. I mean, this is just your very classic feed forward. Can also be very nice to just see how we, for example, introduce the bias, going through the activation step. I think this is a very clean implementation of the neural network code. And again, I think probably if people here have taken PhysSDK, you've probably written your own neural network and are maybe familiar with this part. And also the backpropagation part of the neural network is also probably a bit more familiar than the backpropagation passes of the pooling layers and the convolutional layers. However, it can still be interesting to just scroll through a little. Are there any questions before I continue on? And does anyone want to spend a bit more time on these fully connected layers? I've gone through them a bit briefly because I think when you write your own implementation, or you just kind of want to figure out what the CNN does, it's a bit more of a mystery what some of the other layers do because they're not conventionally covered in the same way that neural networks are. So I'm just going to go through this part a bit faster. And finally, we have the output layer. Here we, for example, will use softmax conventionally in the CNN. However, you can use any output function that you want. And this just acts as the final layer of the neural network. Now, this code base can also be used to just write a simple neural network, or you can feed any type of data into a neural network. For example, in my PhysSDK project, which I did with Greg Haida and Jonathan Hansen, we built a PCA that feeds into a neural network, which was actually a very, we thought we were making something new with like a PCA neural network, but it turns out PCA was actually used like all the way in the beginning instead of convolution. So we actually just went back like 30 years in machine learning history instead of going forward, but that's fine. So here, finally, before I show you guys a bit more of the overview code of the CNN and how to play around with the code base, we've made this optimized version of the convolution code. So as you can remember, we had these nested for loops. It's very inefficient. So how can we increase the speed? How can we make the calculation faster? And there's some very, very interesting ways to do this. Again, this is very like detailed. You don't really have to know about this in your day-to-day life, but it can be interesting because you're using TensorFlow and it goes, I mean, fast, but like, I mean, you still have to wait a while, but it goes way faster than our code would run. So what do? They don't have these nested for loops. Instead, for example, they extract some windows out of the image data. And instead of running a convolution, you simply reshape the windows to have the correct dimensionality, such that the dimensions which have to be like what you care about convoluting, you can line them up and simply perform a matrix multiplication instead. Why this works, at this point, it's beyond me. I developed this code about half a year ago, so I don't remember these details, but it's a very nice way to speed up your calculation, and it's a very interesting way to do so. However, again, as we wanted the code to be readable, you can kind of see further down that it's like there's a point where just like it doesn't make any sense anymore, because you kind of like you have to do all of these transposings and you have to reshape. So it's not that intuitive, but I just wanted to point out that there are ways to really speed up this convolution calculation. And also in the backpropagation pass, you can get rid of the for loops in favor of a faster calculation. But again, it's less intuitive. But it can be really cool to look at the examples of what people do to speed up the code. And also, if you've ever wanted to, instead of applying the networks, actually write your own, I think these optimizations can be really interesting. So here we have the code for the actual CNN class, which we'll use if you want to play around with it. However, most of these are just to add the layers. They have some default functions. We have some pointers. For example, the nodes should be integers, and we have a description just so that the documentation should be a bit easier. However, again, I'm going to go a bit fast through this because I don't think these specific details are that interesting. If you want to build your own, I think some part of this, which is kind of cool, is that the layer structure, let me try scrolling, is that the layer structure allows for an extremely simple feed forward pass. As here, our feed forward method for the entire CNN, convolutional network, pooling layers, fully connected layers, output layer, everything included, just simply runs through a little for loop, which says for layers and layers, just feed it forward. And the same goes for backpropagation. In the fit method, we have some other classic details which might be of interest, such as how to split your code into different batches and how to run it for multiple epochs. And here, most of the methods I'm scrolling through, you might see a bunch of code and they might be a little bit scary, but just trust that most of this is just like helper functions, which are useful, like obtaining the scores or initializing the weights. And for example, a prediction function, which you can use to calculate like different predictions, depending on if we have binary data or multiclass data, etc. And as you can see here, we also implemented our own progress bar, which was a joy to program. It even shows the different like accuracies for validation and training when you program it. So how are we for time, Morten? We're fine with time? Perfect. So when it comes to using the CNN code, I'm just going to run through the short example. So if you want to create a scheduler, you can write anyone. You just pick one of the classes seen above. Again, if you do this, you'll have to scroll up and down a bit, but it's probably going to be fine. And for Adam, you just select your parameters for eta, row, and row 2. You don't have to do this. There are default arguments for the scheduler, but just in case you want to really create your own. And I'm just going to run this. And here we're going to develop a very simple convolutional neural network structure where you add one convolutional layer with one input channel, one feature map, a kernel that's 3 by 3, and we introduce some nonlinearity via our ReLU function. Then we flatten the input and feed it into this neural network structure, which has 30 nodes, 20 nodes, and finally with 10 nodes for softmax. It should be also mentioned that we're using the MNIST dataset, which is a dataset of numbers from 0 to 9, and a bunch of different examples. We're using quite a downscaled. I think we're using a 28 by 28 pixel range because, again, running it through all of these for loops is going to take some time. And if we just run this code, and then here we input the data and do our classic, splitting it into validation and training data, one-hot encoding it. This is just some background which you have to do in order for it to feed into our neural network, which can be a bit of a hassle sometimes because when you implement your own neural network, you're probably implementing it with some idea of like, oh yeah, all of the data is going to be images, input channels, kernel width, because that's the default in TensorFlow, but that's not the case. You have to reshape and reform your data if it doesn't come from TensorFlow, for example, to fit your data. So here, if we fit it, you should be able to see our cute little progress bar, which is making a valiant effort to get a bit faster. But you can also see here that when you fit it, you can run some different experiments. You can select the data set, your lambda, the amount of batches you want, how many epochs, and your validation data. And the score matrix can then be used to plot different like training accuracy and validation accuracy over time, for example. And I think that just about takes us through the example code. Again, just to show off the flexibility of this code, you can just create any structure you want with the convolutional layers. You can use asymmetrical kernels, which are technically even one-dimensional here. You can pool however you want. I mean, this is just like a kind of silly network where we pass it through a convolutional layer, then a pooling network which takes the average, and then a pooling network which takes the max. But this is just to show that you can really play around and use it however you want and use all of the different activation functions. Finally, before I end my part of the presentation, I just want to talk about some additional remarks, which me and Greg thought were interesting, and some further places that you can explore if you want to develop your CNN or just have an interest in machine learning in general. Here we talk about, let me see. Here we talk a bit about the speed of convolution and how to improve the speed with separable kernels, which means essentially decomposing our two-dimensional kernel into two one-dimensional kernels and then applying them instead, which improves, it just reduces the amount of calculations you have to do, thus improves the speed of the convolution. If you remember, I spoke about how we can reshape and transpose the windows of your images in order to increase the speed of it by doing a matrix multiplication using some magic. You can kind of also try to think of the challenge of implementing all of these optimizations on top of each other. Like, okay, you can now extract a window and you can matrix multiply it instead, but if you also want to implement the separable kernels as well into that optimization, it quickly becomes this puzzle of just like, how do you fit all of the pieces to make it go as fast as possible? And I think that can be a really interesting challenge. Furthermore, we did some convolution using the Fourier domain as well. If some of you have more of a background in image, I actually forgot what the word is in English. Image something. Yeah, you can use the Fourier domain instead of doing a convolution, which allows you to use matrix multiplication instead of, or dot multiplication instead of convolution, which can, in certain conditions, speed up your convolution. But again, stacking all of these optimizations on top of each other proves to be quite a difficult challenge. So yes, that was it. The last part specifically were really just for the people who are very specifically interested in this type of work with neural networks. And I think from here, Morten will continue with how to build convolutional neural networks in TensorFlow. Yes, of course.
So that if people have questions there, and also about setting up whether you want to code in TensorFlow, Keras, or you want to So these are, for those of you who want to, let's say, to use these methods of classification of say images. Correct. So this was just one, what we did then last year, that this ended up being one project. And some of you may, if you want to have specific applications afterwards and the project develop, if you're thinking of writing a project like this, then you can make comparisons with, let's say, TensorFlow or Python, and look at benchmarks with these programs, and then have specific, you always need to have some specific data as well as so this is the one part for the project. And I would say that it requires a lot of job. So I would say that in that case, for those of you who choose that, for let's say the deadline before the Easter break, you just simply send in a status report. We have done this and this. This is where we are, and then you write just one final project instead of having two specific projects. Or if you want to break it up, you can do that. But that depends very much. For those of you who just want to make one big project, then we would like to have a status report by the Easter break, so that we can see where you are and give you feedback, obviously. But feel free to ask everything.
Yes.
If you remember the 4 or 5 programs on the HPC resources, do you see any speed up, or is it the same as
We haven't tested it. I'd be interested to see if it would speed up. I don't know how that would work actually. We haven't tested it, but it would be interesting to see. That's a good question. Yes. Thank you. Yes. Yeah. Rigorous testing. Actually, a lot of the check for error stuff we wrote was actually for our own good, just so that we can check when we run the different test programs that they work. Now, the test programs aren't included here. A general, like our general goal was to ensure that our code reaches a certain percentage for a certain data set, and we reach, I think, like a 99% on the MNIST data set, which is what you would expect out of a CNN to be able to perform. So we knew that it was up to the standards in that regard. We checked for a bunch of different bugs using specifically testing environments. So we would also run, we usually programmed in our own editors, but we ran it through, what's the name of the editor? It's PyCharm, which has a specific debugging feature. And the debugging feature in PyCharm allows you to see what happens to each matrix through time. I don't know if any of you guys have used the debugging feature in PyCharm, but it's extremely useful to be able to validate that your code does what it wants. And we also have some test programs written where we just show like, oh, this is what we would expect out of a simple gradient calculation. And then we run our own CNN and we run it through the debugger, and we see that our CNN gradient calculation follows the gradient calculation that we've set up, which we know is correct, if that makes sense. But it's a very good question. This is being my first kind of larger project, which I've done officially as a job. So it was actually a bit of learning how to handle having all of these different Python files, how to set them all up in a package, and ensuring that it's bug-free. Yeah. And yeah, I did review the code yesterday, and I did find a bug. So it's not perfect. Yeah. Yeah. But yeah, thank you for your question. Yes, sir. Yes. Yes. So let me check this for some specifics if I can find it in the code. In the backpropagation, I mean, I know the backpropagation part by heart, and that's simply you keep your weight for every single layer, which it was in the feed-forward part. You just you set a variable kind of globally for the weight, such that in the backpropagation pass you can apply the kernel, which has. I want to find the code so that you have some context to what I'm talking about, because it gets very wordy very quick. But I can find it. Let me see. Perfect. So here at the very start, every single time that you initiate such a layer, we will reset the weights here to be, I think we have just, let me check. Yes. No, wait, the resetting of weights happens here, I think. Yeah, so we use a random weight initialization in order to initialize the weights every time a CNN layer is initiated, and this will become kind of the weights for the kernels of this layer, which we can use in the feed-forward and backpropagation pass. In the backpropagation pass, we use this. We pad. Let me just check that I can find the correct piece of code here. We calculate the gradient for the kernel by doing a backpropagation pass. And again, I'd recommend really reading this article on backpropagation, which is really interesting, where we convolute the X batch and the delta term in order to figure out this gradient kernel, which we use to update the weights being included in the kernel of the matrix of the kernels, the filters you would use in the convolutional neural network. So here you would calculate again the gradient for the kernel, and here you do the actual updating of the weights. And this looks very familiar to the updating of the weights that you would do in backpropagation of a dense layer. In the feed-forward part, I don't think we do much with the weights in the feed-forward part, which also, I mean, would be consistent with what you would do in a regular neural network. So in a sense, it's actually not that different than what you would do in this, like in a dense layer.
So the weight of this assigned to the 3x3 matrix?
Yes, every single filter is a combination of weights which are learned. And this really is the core of the CNN principle, that you have these filters which learn features, and this occurs via the learning of weights. Yes. Does that answer your question sufficiently? Yeah. Yes. No worries. So our process for like when we started our project, how did we think about building the CNN? We first looked at a bunch of different resources that already exist. For example, how do TensorFlow do this? How does PyTorch do this? And then we immediately saw this layer structure being very persistent. And we also thought it's intuitive, it makes sense. We first programmed this very typical network of, for example, implementing max pooling as being the most dominant form of pooling. We created this for loop in a more simpler sense, for example, the convolution step, without having stride included. We had this very like bare bones structure to begin with, and then built on more features, which then kind of forced us to generalize the code. And when we generalized the code more, it became easier to implement all of these additional features. If there's any specific questions about like steps of the process, feel free to ask, of course. Yeah. But I think the big learning step for me was just like you like just see what people have done before you, and then try to understand what parts make sense and what parts don't make sense. Yeah. Are there any further questions? Otherwise, I see that the clock has become 11, and I don't have the authority to do this, but you all have 15 minutes break. Yeah. Yes. Yeah. Yes. Yeah, and thank you guys for having me. So yeah.
Feel free to ask your questions.
That'll be us.
Yeah.
So the idea first is to give you a kind of bird's eye view on the recurrent neural networks and what they are. So if you now think back to what we have done with convolutional neural networks and neural networks, one of the assumptions which is often made about the data we feed in and the data which we get out is that these data are uncorrelated. So that means an input which you give can be perceived. If you have a probability distribution which describes your data, you would describe them as independent and identically distributed. So if you have a probability distribution for your input and for your output, you would assume that these data which you're analyzing, they are not correlated. Okay? So this is often in statistics is something which is shortened to IID. Now, when you look at a recurrent neural network, on the other hand, the data are extremely sequential and they are built upon each other. So that means that this assumption, which we have typically used when we look at neural networks, convolutional neural networks, and many of the other types of methods which you will encounter, this actually breaks down. The data are typically very much correlated, and often, and this is the kind of application where I come from, we are thinking of a timestamp on the data. So if you're analyzing data from a stock market, you know that this is something which evolves with time. If you're looking at differential equations, if there is a time component, you know that this is something which evolves with time. However, you can have data which do not do that. So if you're looking at language models, then this is not the case because you would have data which are not necessarily perceived as sequential. So the emphasis here is mainly, and with the examples, are mainly going to go in a direction which favors people for more the what we might call the physical sciences or the natural sciences, where the solution of differential equations and how we can use recurrent neural networks as a kind of extrapolator. So just to give you an example, one of the things which I've been studying with recurrent neural networks and similar methods is the solution of fission in nuclear physics. So I come from nuclear physics, and when you do fission, you actually solve a time-dependent set of equations. The problem is that these time-dependent equations which solves quantum mechanical problems are extremely time-consuming to deal with. So you would typically solve this for some few time steps, and then you can think of you using every single time step as an input to a recurrent neural network. You train the network, and then you extrapolate to time steps, or times, which were not included in the usage of your favorite differential equation solver. So that means a recurrent neural network becomes an extrapolator. So that's a typical application which you could use in the natural sciences. Now, I know that some of you want to apply this to large language models. So the recurrent neural networks were together with something which is called, it's a slight modification of the basic structure, which is called long short-term memory, was one of the basic building steps in language or natural language processing. So this is a huge area of application, which I will not touch upon. On the other hand, if you look at the textbooks which we have recommended here, the textbook by Rashka has actually several examples on how you can use recurrent neural networks to analyze language or text. So I invite you to take a look at that one, because these are things which I will not cover in the lectures. So the demonstration next week will focus more on applications to classical natural science problems. Then the same thing applies also to Foster's textbook. So you have one with PyTorch and the other one which implements basically the same type of data with TensorFlow and Keras. So depending on which language you prefer or which setup you prefer, you can use one of these books. Actually, Sebastian Rashka's book has also more text, which explains some of the basic mathematics. And if you click on these links, the links which you have in the notes here, you are directed to their GitHub sites. And from their GitHub sites, you can pull down the Jupyter notebooks for every single chapter. Okay, so as I said, if you think of feed-forward neural networks, they are normally not designed to handle sequential data, where the order actually matters. As I said, the assumption is often that the data you plug in can be treated as independent and identically distributed data, if you know the probability distribution. So this is clearly one of the limitations, and it's also one of the limitations with CNNs. And this is one of the reasons why these recurrent neural networks have become so popular. And they have been extremely popular for the studies of time series data, natural language processing, speech recognitions, and several other problems for which the order of the data is crucial. So the types of architectures which we're going to look at, they vary a lot, and we are going to discuss some of the more popular ones. So, and the examples and the way we are going to present the analysis of the data will be using either TensorFlow or PyTorch. Now, let me show you one simple example of an RNN here. So let me, before we move on, so that you can get a little bit of the basic philosophy here. Here we go. So this is a typical setup with TensorFlow. So I'm importing, actually here I'm importing everything, but I'm going to use what's now called a simple RNN. And later we are going to look at these long short-term memory and then the gated units. I'm importing the optimizers, the regularizers, type of data sets, etc., etc. So what I'm doing here is simply to set up a type of vanilla problem. And as you can see, I'm setting up a sine function with 1,000 points. So I have 1,000 points, and then I'm going to use the 800 first points to train the recurrent neural networks, which means that the next 200 points are going to be my extrapolation of the model. And then I want to see if I can fit the sine function. So one of the places where these do pretty well are if you're dealing with regular features. So the case we're going to look at next week is about a more chaotic system, which is described in the project. And there you will see that we will not do that well. So if you run this case here, the typical way you would run this, so I'm setting up my train data. These are the first 800 points. I have my test data, which are the next 200 of the 1,000 points which I have. I'm setting up a sequential model. I'm setting up for every single RNN. I'm using 32 units. And I'm using the ReLU activation function. I have the mean square error because I'm fitting a continuous function. And I use the root mean square propagation. I could have used Adam. I could have used any of the other ones. Then I plug in my train data. I use 100 epochs. And then I make a prediction and see what I get. And when I now train the model, you can also see the number of parameters I have in my simple RNN model. I have a dense set of layers. So the total number of parameters is not that big. And when I train it now, you will see something. After all the training, you see that the loss function is getting pretty small. And I'm typically running with an error which is 10 to the minus 4. And the yellow line here is actually my reproduction of the data. And after 0.100, after here, I'm plotting my prediction. And my prediction is also pretty good. Obviously, if I were to rerun this, so this is a typical example on using an RNN where you have sequential data and you train it with a specific input and a specific output in every step. So this is what you want to reproduce. So you train a network to do that. And then you make a prediction. So you can think of this as an extrapolator. And it works pretty well when you have a harmonic oscillation like a sine function. If you have a slightly more chaotic results, it may not work that well. And you will see that immediately if you add some random noise here. Then you will see that your prediction is not the very best one. So if you now remember that we had a mean square error of something like 10 to the minus 4, you can see now that the so-called loss function here, which represents the mean squared error for these different epochs, is on the order of something like 10 to the minus 1. And this is what you get, where the yellow line, or the yellow color here, is my prediction. So with the noise and these irregularities, it's much more difficult to train the model. But in situations where you don't have, let's say, chaotic motion, or you're solving a differential equation which exhibits pretty regular patterns, this is doing pretty well. So this is one of the applications. And this is the type of application which I will discuss in more detail next week when we look at how we can program parts of project number 1. One of the parts of project number 1. So let's go back to the slides. I always have to find back my, so let me just do that one, just a moment. Sometimes these notes actually tend to disappear. Okay, let me just go back to the Jupyter notebook then. Just a moment. Yeah. Okay. So let's switch over to the week which we have now. So one of the things which after this simple equation here, one of the things which I wanted to look at is a simple example. And the thing which we will see now is that if we have typical data where we have oscillations, we will typically do pretty well. We will see that they can settle down to point attractors. They can behave chaotically. It can. could potentially learn to implement lots of small programs that each capture nugget of knowledge and run in parallel. The thing you will see very quickly now is that the computational needs are pretty large in setting up an RNN. The basic overview of an RNN, which we now are going to break down in terms of a famous differential equation, is something like this. So we are going to introduce much more this kind of graphical representation, because this is something which will be useful later when we are looking at generative models. So you could think of you having some input. This is the way it would be set up in a standard feed-forward neural network. You have some hidden layers, and it produces an output. In our case, on the other hand, what you will see now is that there is some kind of recurrence. So you would have an input at a given time. This gets massaged through some hidden layers where the black magic takes place. And then you get an output at a given time step. But let's try to break this down in something which you have seen before, because that serves as a useful example, which is going to link with the applications next week. So let's take a quick look at that and switch to the whiteboard. So what we're going to look at now are how we can represent the solution of Newton's equation as a recurrent neural network. So let's take a look at the famous equation here. So we're going to look at Newton's equation of motion. And we are going to have something which runs like a mass of the second derivative. So this is the acceleration, plus some damping factor over dx dt, plus x of t is equal to some applied external force. This is something which I assume everybody has seen here in one of the basic introductory courses in mechanics. Or this may bring back some memories from high times in high school. So the equation which you see here has a damping factor, which is a velocity-dependent term. And then there is some constant here, which may represent some dissipation or friction term. We have the mass, this is the acceleration term. And then we have a harmonic oscillation here. So we are thinking of a particle which oscillates, or an object which oscillates harmonically. So that's why we have this x of t term. There is some applied external force here, which keeps the object moving, because else this would come to rest if you didn't have this term here. Now, typically, the way you solve this is to split it in two differential equations. So you would rewrite as two coupled first-order differential equations, as two first-order differential equations. And that means that I have an expression for the velocity, which is just a derivative of position. And then if I take the next one, I have an expression for the acceleration. So which gives me m times dv dt, because we know that the acceleration is the time derivative of velocity. For those of you who are not too familiar with Newtonian mechanics, we have the velocity plus this x of t is equal f of t. And then what is normally done is that we scale the equations. So we would introduce a dimensionless time. When I scale them, what I would be left with then, when after I have scaled the equations, so let's do that. And I'm going to be a little bit sloppy with notation here. So my time t is not going to be labeled with a time tilde, but it's just going to be time. But we are going to simply let t go over to a dimless time. And I use the same variable. So these are just dummy variables, right? So I can call them whatever I want. And then I scale the equations, and that means that I get an equation of the type of d of x dt, second derivative, plus a new constant I call for gamma. And then I have a dx dt, and I've scaled it so x stands by itself. Actually, x has a constant in the previous equation, which I omitted. So there should be a constant k here in order to do this correctly. There should be a force which is modified, but I'm using the same label. So these are now scaled equations. And then I simply get v, which is dx dt. And then I have my dv dt, which is equal to f minus this parameter eta times v minus x. Then we discretize, and then we implement, for instance, Euler's method, which is the simplest possible way of approximating the Taylor expansion around a time t plus delta t. So we discretize, which means that x goes over to x of I, which is the same as x at the time t of I. This t goes over to t of I, which is equal to some time t0 plus I times a delta t. That's a time step we've chosen. And then I have my v, which goes over to a v of I, which is the same as a v of t of I. Then I use Euler's method, and then I have the following equation here. And with Euler's method, what I get then is, and now I'm looking only at the velocity. I'm not interested in the position, only v. I mean, obviously, when you solve it, you need both. But now I'm just looking at the velocity. So what I get then is that I have v of I plus 1, which is equal to v of I plus delta t. And then I have my derivative of dv of dt. And this is at v equal to v of I. So there should be approximations here. So this is the approximation because we have higher powers of delta t, which we leave out. You can rewrite this now in terms of an f of I plus 1, which is equal to v of I plus delta t. And then we plug in the expression here. So we have f of I minus, and then I have v of I times this parameter gamma minus x of I. This is a discretized equation, which I then integrate on. Now, what I do next now is that I redefine this as a new function. So I'm going to redefine this as a function which I'm going to call for h. And this, I use h because this is going to refer to hidden layers. And this contains now x of I as input. It contains v of I, and it contains this variable f of I. Okay? So there is a function now which contains the values v of I plus the first derivative, and which I just now put in terms of a specific function h. And then you see also that the v of I is now going to be equal to v of I minus 1 plus delta t, and that has f of I minus 1 minus v of I minus 1 times gamma minus x of I minus 1. And this is nothing but h of x of I minus 1, v of I minus 1, of f of I minus 1. So if we then go back to this v of I plus 1 here, you see now that this can be rewritten as h, and then I have my x of I. But now I could now place this, and I'm going to call this an h of I minus 1. So you have an expression for v of I, which is h of I minus 1, and then I have f of I. So that means that I have information from my previous layer. Now, one way you can train this, if you want to train it with a feed-forward neural network, because now you're going to generate solutions. So your final V is going to be a vector which will contain V0, V1, up to some final time V of n. So we can now rewrite this in the following way. So graphically, and this is pretty common to do now, we have a sum V0, which now feeds in to a function, which you can call for H0. So if we go back to the definitions which you have here, you see now that this would be actually H of I. If we use this notation, so I would have an H of 0. So this feeds in V of I plus 1. Now receives an input from this function H of I. So V0 feeds in here. And now you could write this as something which gets an external input, X0, and F0. So let's simplify further now. So we are going to make some further simplifications. I'm just going to put this F equal to 0. So that means that the only thing you feed in, so this could be just a damped harmonic oscillator if you want to. And this produces an output, which is V1. Now this feeds again into a new function, H of 1, which gets an input here, X1, and that produces an output, V2. And this goes all the way up to the final time of an H of n, which gets an input, Xn, and which then produces a final output, which I call for V final here. Okay? So this is a typical way by which I could now set up my solution of the differential equation. So in this particular case, the only thing which I'm doing is simply to solve my differential equation with Euler's method. And in every time step, I get to evaluate this function here. That gives me the update, which is my output. And what you could think of now, if you want to make this a little bit more fancy, is that you could think that you now have here, you have some observations. So you would feed this result, V1, into a cost function, a C. So every time here, there is a cost function. So you make a comparison with something. So the comparison with something is now some measurement which you have made. So we could call this measurement just some V of 1 prime. This is our measurement. It could even be the analytical solution of the equation. So suppose now that you are solving this equation here with the approximative method, and Euler's method is something nobody brags about. I mean, it's just something you use as a quick and dirty way to do some calculation back on the envelope. You would normally use much better method for solving the differential equations. But you could think now that you have made either some observations or that you are including some kind of analytical solution. So every time here, you would now have an analytical solution which is fed in, and then you have a final V final here, which is fed in. So this is a way to now actually represent what you're doing with a traditional equation solver. However, what we can do now is to start to think of what you see here now as a setup for a neural network, or better, a recurrent neural network, which means that in the training now, instead of you having your fantastic differential equation solver, which gives you this function every time you update your time step, you replace this with the parameters of a neural network, which you then want to train. So you see the basics. So this is just one way. I mean, I think I like this example because it gives me a kind of intuition, since I come from this kind of monothematic differential equation world, right? And it's nice to actually make that kind of link, because you can now think of replacing everything you see here with the parameters of a neural network. So that means that you will train now weights and biases which connect some kind of input. So this could be a kind of external force which is applied to your system. A typical time series is exactly that. If you think of medical research, you would often take a blood test at a given time. So you would have some input, you extract some output, and then you repeat these kind of measurements on the patients over time. And then you want to analyze how, let's say, the blood pressure or other things develop as a function of time for a given patient. That's another example of a time series. Or if you just want to be very, very, simple-minded and use a standard feed-forward neural network, what you could do then is that you could train your neural network with this as input and this as output. And then you move on to the next step, and then you have the previous velocity, V0, as an output. And then you have the next one as an output, and then you have V1 as input, V2 as output. And then next time, V2 as input, V3 as output. And then you would train a standard feed-forward neural network that way. The drawback with that is that the memory, which you would like the system to develop, is not there. So when you connect a network like this, there is a memory which you keep track of. So that means that you know exactly what happened previously, and that influences what happens next. If you just train a feed-forward neural network with a V0 as input and a V1 as output, and then you just repeat that, there would be no connection between these terms. You see the difference? So with a recurrent neural network, on the other hand, we are trying to link these different components. And that's one of the essential differences between us making a training of a differential equation solver. So suppose you solve your differential equation. Now you would have these solutions at different time steps. So one previous time step, input to the network, you train with the output, and then you move stepwise like this. But then you lose the memory. So that means you are interested in actually gaining information about this function and what that is doing. So if you go back to the project, that path which deals with the solution of differential equations or fitting differential equations, you will notice a difference when you use a recurrent neural network and a feed-forward neural network. Okay? So let's move on a little bit and try to make this a little bit more schematic or more general. So I'm going to set it up in the following way now. I'm going to replace variables. So I'm going to keep this x0, but I'm going to let my v become a more general output variable, the y of I. So this is the output at a given step. Which I call t of I. So keep in mind that this does not need to have a timestamp. When you're looking at large language models, there is no timestamp. So it's very easy when you think in terms of time series to actually introduce a timestamp. That's intuitive. So what you would do then is simply now to have some input. And let me find the right figure here. So I have made several figures, and then we're going to switch over to, so we are going to actually rewrite it in a slightly more general way. So there's going to be a function h, which now keeps track of the memory. So this is the compact way by which you would put it. And then you have some input x, and then you have some output y. This is a typical way you would now set up this kind of recurrent neural network. When you now break it down, what you would have would be some h0, which feeds into some h1, this receives some input, which I just call x1. Now, this input is going to be modulated with some weights, so that introduces parameters. So keep in mind now that now I don't have these nice recipes, which links the previous step with a new step. So what I'm doing now is to replace everything here with a neural network, which means that now there will be some parameters, which I'm going to call here for a parameter u here. So that means that my input at a given time, this is a kind of external probe, which affects the system, is now scaled with some weights, and that is fed in to this H1, which you can think of as a neural network. It doesn't need to be a simple neural network. It could be a convolutional neural network, okay? So what you put in here, it depends very much on the type of problem you're looking at. So it receives also information from the previous step. So there is a memory here. This is the standard way of training a recurrent neural network. So when you see in the TensorFlow, what they call simple RNN, this is actually a straightforward recurrent neural network with memory connecting every single step. Okay? So that means that this one is now going to produce some kind of output. This is your hidden layer where the black magic takes place. And this is now connected here with some vector v. This produces an output, y. Now this output, so I'm never good actually at planning my images, but this one feeds in to a cost function or loss function. So let me just use an L here, because it's common to use this as a loss function because it stands for an individual contribution at a given step. And here you would feed in your target value. And I'm going to call this target value for a y tilde. And we have to put in a 1 here because this is our first step. And you could think of this y tilde as a measurement you have made. So what you're forcing now through these different parameters, you're forcing the network to find the best possible representation of the inputs and the outputs. Now, what you would have then is also a set of parameters which connect one hidden layer from a previous step with the next hidden layer. What you will often see now is that this becomes, if you have many measurements, suppose you have thousands of measurements, it means that you would have to store matrices, which can be pretty large, many, many times. So what is often done then is that you would train in the beginning and change the weights and the biases in the beginning, and then use the same weights for the rest of the training. So I'm just going to use a symbol V. Actually, this letter which you see here, this is a letter, my attempt at the letter U. It looked like a W, sorry. Then this feeds into the next one. So we have a new weight, and you continue with an H2. You may have some external probe, which feeds in an input at that stage. In our case, this could be the value of X as we had in the differential equation. And then we have a U again. We produce a new output. So we have a V here. So this will be a Y2. This feeds into a function, which could be a mean squared error, like in that simple example I showed you. And this has a Y tilde 2 here. And this continues all the way till the final time. So we end up with a H of n. We have an input X of n with a weight. This is still a letter U. There is a W here. We get a V set of weights. And we have a Y of n. And that feeds into a cost function. And this has a target value Y of n tilde. So the training now, which takes place, is a training at each step. So the feed-forward pass is pretty easy to imagine because you would just initialize the weights and the biases for the matrices W, U, and V, and then you make a feed-forward pass. In every pass, you produce an input to this function. So this function here should also have a label 1, and we would have a label 2 here, and a label N here. So we would then collect all these loss functions into a final cost function, and that is the function which we would take the derivatives of. So the feed-forward pass is the same as you've done before, except that now it's more complicated. So when you've done the feed-forward pass, then there is obviously the chain rule, which comes back again. So we're doing a back propagation. And that's the way we will train the weights and the biases in the different layers. Now, there are many, many nasty pitfalls in training an RNN. So one thing which happens is so-called exploding gradients. Because if you think back into a standard neural network, if you just have one single layer, you're just calculating some few gradients. But here, we're actually calculating gradients in every step. So that means that we are multiplying these matrices W many, many times. And clearly, if some of the gradients start increasing, then this matrix times that one, et cetera, can quickly lead to huge values and then exploding gradients. So that's one of the big problems in training these kind of recurrent neural networks. So what we need to do now is actually to set up for the feed-forward pass. So in training this network, in training, we have a feed-forward pass. And in each stage, what we are going to do now is to have a function C of t, and I'm putting t of I here. So that's a step t of I. That is going to be equal to this U matrix multiplied with this X t of I, plus this matrix W, which multiplies the input from the previous time step. So this is again a t of I minus 1. And then we have some bias parameters. So this is a vector of parameters which is added in case these matrices U and W are occasionally set to 0. Then we produce this new value, H of t of I, which is then given by some activation function, some sigma for that specific layer. This could be a real function, it could be a tan H, could be a sigmoid, etc. And this takes this Z of t of I as input. So often in recurrent neural networks, people tend to use tan H functions. I will come back to why. So often, so we will discuss that a little bit more next time. Tan H as an activation function. Then I produce a new output R of t, which is the same as now this matrix V. If you go back to the drawing which we had here, so I'm producing now the output from this. I'm serving in here. So I have this one times plus this one times that. Then I'm having this matrix V, which now feeds in to the final value Y of t. So I have my V of H of t of I plus a new bias. So this is a new bias parameter. And then I produce my final output. And the final output is going to be a Y of t of I. And that is given by a new activation function, which could be the same as before. And that takes this R of t of I as input. So this is again my pretty crappy attempt at making the letter R. But you see, basically, these are the parameters which we have to deal with at every step. So this means that when we now are going to implement backpropagation, we are going to have to calculate the derivatives of the cost functions with respect to the weights, the biases, which now appear in these different quantities. So the feed-forward pass is exactly as before. We initialize the weights and the biases, setting them to, let's say, randomly distributed according to a Gaussian distribution with small values. And then we make a feed-forward pass. In every feed-forward pass, we calculate the loss functions. When we have done that, we have the next step, which is a backpropagation step. So the next step is the backpropagation, but now it's backpropagation in time. So that's the difference from what you had before. But in essence, it's again, this what we might call in a very, very arrogant way, this kind of high school mathematics with application of the chain rule. So this is backpropagation in time. And I see that my time is running out. So next Tuesday, we are going to go through the backpropagation in time. We are going to look at why this recipe, even if it's very powerful, becomes extremely time consuming. It can lead to exploding gradients, and it leads to huge memory requirements. In particular, if we want to store all these weights and biases. So what often happens then is that we have to find strategies to keep information about the memory, but at the same time, avoid to store as much as would be required if we now allocate space for every single time step which we have. So in principle, this looks very nice. It's very powerful if you can train it, but it becomes unwieldy when you have lots of data. So next time we are going to look at strategies to circumvent that. And at the same time, we will look at how we can study the solution of differential equations using recurrent neural networks. Questions to the RNN part? So this was more to give you the kind of overarching view, and then we are going to do more details next week. And after that, we begin with autoencoders, which will be the last topic before the Easter break. And after the Easter break, we do generative models with variational autoencoders, GANs, and diffusion models, etc. Any questions so far? Yeah. Yeah, absolutely, absolutely, absolutely. Yeah, yeah. Those. Okay, see you guys next week. And there is a lab session on Thursday.